mobile detection of strawberry plant diseases using MobileNet version 3 and Kotlin. The authors of this article are Rodríguez-Sandoval, Ochoa-Ornelas, Raquel, and Rodríguez-González, Ansel, Yoan. For the introduction, the strawberries are a key crop for the Mexican agriculture and are in high demand internationally, placing Mexico among the top 3 exporters, with revenues of close to 400 million pesos in 2020, especially in Michoacán, Baja California, Jalisco, and Guanajuato. However, pest diseases such as powdery mildew and others threaten the quality and quantity of production and may even pose risk to the human health. For this, the precision agriculture integrates robotics, remote sensing, data analysis, and image processing to optimize crop management. Image processing combined with machine learning enables fast, accurate, and affordable detection of pests and diseases by comparing affected and healthy plant areas. Although hyperspectral methods provide high precision, their costs limit the uses. Thus, the mobile devices and visible spectrum imaging offers accessible alternatives for rural farmers. Lightweight CNN models like MobileNet version 3 have shown efficiency for on-device disease detection in Android application using TensorFlow Lite, supported by specific strawberry datasets for realistic training. In the methodology, a dataset of strawberry images with the several diseases annotations obtained from the Kaggle was used, containing labeled image and allowing for segmentation and classification. These classes are angular leaf scourge, powdery mildew, blossom blight, healthy, and leaf scourge. The preprocessing of the image. The image was normalized to values in the range of 0 to 1 using the next equation, where I represents the pixel matrix of the original image, and Imin and Imax correspond to the minimum and maximum possible values. This goes to 0 and 255 for RGB images. In order to strengthen the model in real-life conditions, such as variation in lighting, orientation, and leaf scale, data augmentation techniques were applied with the following parameters. For the techniques, we have random rotation in minus 25 degrees and to 25 degrees, horizontal reflection, random zoom, and displacement. The MobileNet version 3 model was implemented in its small and large variants, previously trained with the ImageNet dataset. Based on this architecture, a transfer learning process was carried out with a partial fine-tuning, freezing the last layers and adjusting the remaining layers of the bottleneck and the classifier. The model performance was evaluated using the metrics precision, recall, accuracy, and F1 score. The model was lately exported to a TensorFlow saved model and converted to a TF Lite and evaluated in-device to measure latency, memory usage, and power consumption. The main components in the application architectures includes the UI, made with Kotlin and Jetpack Compose, a camera layer, the inference model, and the storage, in this case a room database. For the results, the preliminary results obtained with the MobileNet version 3 architecture show significant performance in the classification of leaf diseases. It is important to note that the quality and condition of image capture have a significant impact on model performance, especially in classes that represent mild symptoms or or are under non-uniform lighting conditions. During the training process, MobileNet version 3 achieved an accuracy of 82% of the validation set. The model also obtained precision values of 91%, recall, and of 22%, and F1 score of 86%, demonstrating an adequate balance between sensitivity and accuracy in predictions. The most frequent classification errors highlighting gradient confusion in the left scorch class, followed by angular left scorch, were possibly due to its high visual similarity to other diseases and the model's limited ability to represent subtle features. These are the results for the MobileNet version 3. For the angular left scorch, the precision was in 90%, the recall in 93%, and the F1 score in 85%. The powdery mildew, the precision was in 92%, the recall was in 94%, and the F1 score was in 87%. For the blossom light, the precision was in 93%, the recall in 96%, and the F1 score was in 88%. For the healthy class, the precision was 89%, the recall was on 86%, and the F1 score was on 86%. This class was the lowest of all. For the MobileNet version 3 overall results, the accuracy was on 82%, the precision in 91%, the recall in 94%, and the F1 score on 86%. These are the screens of our application. The first one is the main screen when you open the application. Later, you have to select an image. That's the second screen. After you select the image of the plant, you just need to press the last button, and it gives you the classification for the image. For conclusion, developing an Android application in Kotlin that incorporates MobileNet version 3 and TensorFlow Lite is a feasible and effective solution for early detection of diseases in strawberry plants, with a pipeline that includes fine-tuning and device testing. A practical support tool for producers can be achieved with the adequate latencies for field use.